Okay, so let us do a recap of where we are. Okay, so we have been talking about convolutional codes. Okay, so the way we have been approaching this is to first talk about the encoder. The encoder is nothing but shift register, right. So, shift register based encoder. Okay, I gave you a very simple example. I showed how you can clock bits in and then clock bits out. Okay, you get a shift register as the encoder, and then there are various representations for the encoder. For some reason Windows wants to update. What should I do? Well, I can't cancel. Oh, postpone. Okay. So I thought this taskbar was supposed to be locked. I guess the update is so crucial that it does not care about. It's still locked. Okay. All right. So the encoder, and when we spoke about various representations for the encoder, one was the state diagram, and the only drawback in the state diagram was the time axis was missing. So a better representation turns out to be what I pointed out as the trellis diagram. Okay. So usually the shift register will have one input stream, and let us say some n outputs, okay, and the number of D flip flops is also known as the memory. So memory is going to be some mu. Okay. So if you make a state diagram with this shift register, this shift register encoder, you are going to have how many states? 2 power mu states. Okay. And how many branches out of each state? How many branches out of each state? Two branches out of each state. Okay. How many branches into each state? 2 branches in and out of each state, right. So it has to be that way. Okay. In and out of each state. Okay. Where will the n play a role? Basically each branch will be labeled with 1 bit input and a stroke and n bits as output. Okay, so that is the branch labeling. And trellis diagram, since we explicitly have time playing a role, we have to first specify the number of input bits. Okay, so we usually keep it as, so let us say some k input bits, okay, plus. Okay, so is that enough? Can we stop there? No, we have to terminate the state back to the all 0 state. For that you need mu termination bits. Okay. So the number of output bits n will be equal to what? Small n times k plus mu . Is that right? Number of output bits will be small n times k plus mu. Okay. So the actual rate k by n times k plus mu. Okay. So if k becomes very large, roughly 1 by n for large k. Okay. So 1 by n is known as the design rate of the encoder. Okay, so the actual code rate will be different. Okay, so that is the description of convolutional codes. So the way we are looking at it, once you fix the number of input bits as k and look at all the output bits you got, okay, can I think of this code as a block code? Okay, for every k bits of message I am getting n bits of output. Okay. If I go ahead and exhaust all the 2 power k possibilities, I will get 2 power k code words, n bit code words. Okay. So, actually in this description it is also an n comma k block code. Okay. Right, there is nothing wrong with thinking about it that way also. Okay. So, you can think about it as a n comma k block code. Okay. You can in fact come up with a generator matrix for it, a parity check matrix for it, all that you can do. Okay. There is nothing wrong with that. Okay. Except that we are describing this block code in a very simple way using simply mu d flip flops in a shift register implementation of the encoder. Okay. You do not have to describe it in any other complicated way. Okay. So, it is a very simple description for the encoder itself. Okay. So, essentially you can also think of it as a block code, there is nothing wrong with that, except that it is traditionally called a convolutional code because of obvious reasons, right. This is a shift register, so it has an impulse response. So, you can think of the output as being a convolution of input and the impulse response of the shift register. Okay. So, for those reasons it is called convolutional code, but in actual operation it will always be a block code. Okay. So, will it be a linear block code? Yeah, it will be a linear block code because it is a linear linear shift register. So, add 2 inputs, if you XOR the 2 inputs, the corresponding code words will also XOR. Okay. So, it is all, every operation is linear there, right. Every code word bit was written as a linear combination of the inputs, some inputs, right. So, it does not matter how else you think about it, it will be a linear code. Okay. So, this is just a different way of thinking about that problem. Okay. The trellis representation on the other hand has a complexity of 2 power mu. Okay. So, it is referred to as the complexity of the trellis. It is one measure of complexity, it is the most common one. 2 power mu, the number of states that you have at any given stage, is the complexity of the trellis. Okay. It turns out the trellis plays a key role in decoding. I will describe why, it is easy to see why it will, but so because of that the complexity of the decoder is limited by mu. So, even if you increase k to a very large number 1000 or 2000, you only have a complexity of 2 power mu and not 2 power k. Okay. So, you remember that was our fear when we did ML decoding, right. Complexity always became 2 power k. Okay. And if k becomes 1000, then you have no hope of implementing it. Because of the trellis, for any k you only have a complexity of 2 power mu. Okay. And the decoder also becomes only 2 power mu complex, and that is the major attraction of convolutional codes. Okay. Otherwise, if you look at it in terms of minimum distance, these codes will not be that great. Okay. And in fact, more than the minimum distance, I will point out later, the number of minimum distance code words is fairly large for convolutional codes, and that is a problem when you implement them. Okay. So, as block codes they may not be that great, but since they have a decoder, they have very interesting characteristics which we will see later on. Okay. So, the next thing I am going to point out to start with is the decoding. The decoder, the ML decoder. So, we will talk about the soft ML decoder. So, for the soft ML decoding, as usual we will be using BPSK AWGN. Okay, remember BPSK is 0 going to +1 and 1 going to -1. AWGN will be noise distributed as normal AD, right. So, that is our standard assumption. There is also a hard decision ML decoder, okay, in which case the channel will be a binary symmetric channel, right. So, that is what we will be using. So, that is what we have used in standard as a standard for hard decision decoding. So, I am not going to describe that. Okay. So, it is quite simple. Towards the end maybe I will point out how that works, but we will begin with the soft ML decoder. Okay. So, there is lots of notation that needs to be built up. Okay. Finally, the decoder is very simple and you will intuitively get a very easy idea of what is happening as we go along, but initially we need a lot of notation to make sure that we do not slip up with the description of the decoder. Okay. So, let us do that notation. Okay. So, my input u is going to be, I am going to start with, shall we start with 0 or 1? 0, okay. u0, u1 all the way to uk -1, and then I am going to have some termination bits. So, I will drop that. Okay. So, if needed we will come to it later. Okay, so for now these are the input bits. Okay, so these are going to get encoded into a code word. Okay, so this is the convolutional encoder. I have this habit of drawing the box first and then writing inside. So what I write inside tends to get really cramped. So sorry about that. Anyway, I think it's clear enough. So the encoder is going to put out now capital N outputs. Now I am going to group these outputs into so again, okay, so we will always fix a rate half code. Okay, if you have a rate 1/4 code or 1/5 code, it's easy to extend this. Okay, so we'll have a rate half code. So in for each input bit there will be 2 output bits. One of them will denote as, let's say, some what have we been doing, V10, and the other one is V20. Okay, so let's do that. So the output will be the code word, so maybe I'll call it C. So the code word is going to be, I'll call it as C0, C1, so on till C, it's going to be K plus mu minus 1, right? It will go all the way till there, and each Ci is actually what? It's going to be V1i and V2i. Okay, so it's actually a vector. Is that okay? So this is the output, and then as usual you have BPSK, and then you have the AWGN chart. Is that okay? Okay. So what we get here, likewise I am going to call as a vector R, and this is going to be R0, R1 all the way to Rk plus mu minus 1. Okay, and then each Ri is what? It's going to be 2 things. It's going to be Ri1, Ri2. Okay, corresponding to what was received for each thing. Then I think we'll stop there. That's enough notation. Okay, so this is the setup. Okay, so given this vector R, I have to now do a decoding. Okay, so Windows is insisting that it will update. So what do we do?
Yeah. 4 hours to 4 days.
Oh, 4 hours. Oh wow, everybody knows exactly how to do that. And it's been ages since I've used Windows actively, so actually I've never used Windows actively except for this lecture, of course. So is it going to go down on its own or what? The task bar won't? Okay. Wow. That's some resident Windows experts. Okay. So the decoder is going to put out U hat. That's going to be once again U0 hat, U1 hat, UK minus 1 hat. Okay. So there is a tendency to get lost in the notation, and some of you might get lost in the notation, but I mean, hang on, there is some simple description towards the end. Okay. So when you are doing soft ML decoding, what do you have to do? It's very clear what you have to do, right? In BPSK AWGN, when you have to do soft ML decoding, you have to find that code word which is closest in a certain distance. What distance? The Euclidean distance, right? So you have to compute that and find the closest. So the task is pretty clear, and we can write that down. We can write that down without too much of effort. Okay, so soft ML decoder is going to do this. It's going to say U hat is argument of minimum. So here is where the notation is going to get a bit messy. So, I will say u over all u what the Euclidean distance between r and u, it is not u. Okay. So, I have to do a lot of conversion. So, I am going to write it as 1 minus 2 v squared. Is it okay? So, u will belong to all 0 1 k, okay, and v will be c, right, I am sorry, I have been using c. So, sorry. Okay, so, c is what should we think of as c? C is the code word corresponding to u. Okay, so, it is the code word for u. Okay. So, that is the notation. Is that okay? So, the task clearly is to compute this Euclidean distance for all possible inputs. So, how many Euclidean distances will you have? 2 power k. Okay. So, it looks like you will have to compute all of them first and then compare with each other and find the minimum. Okay. So, that is the brute force soft ML task, and that we saw before. Even for the linear codes, it is hard. Okay. It is not going to be very easy to do, it is going to be exponentially complex, 2 power k complex. Okay. So, it turns out because of the trellis you can do it sequentially as opposed to in total. Okay. So, this task of doing the minimization can be done sequentially. Okay. So, that is the idea in the decoder. Okay. So, the efficient implementation of soft ML decoder for convolutional codes, it is called the Viterbi algorithm, after the person who discovered it, or well, the person who came up with it first. Okay. And we will describe that next. This is basically efficient implementation of soft ML. For convolutional codes. Okay, using the trellis obviously. Okay. All right. So, we will begin by looking at this expression r minus 1 minus 2 c. Okay. So, this 1 minus 2 c is a bit of a pain to carry over. So, I will simply use s equals 1 minus 2 c. Okay. So, this s expression we will use, this is basically summation I equals 0 to k plus mu minus 1, right. What should I put inside the summation? Okay. So, remember Ri is actually a vector, okay, and Si is also a vector. It has 2 entries because I have assumed a rate half codes. If rate half code, if it is 1 by n, then it will have n entries, but it does not matter. So, since we have assumed rate half, this is a slightly simpler situation. So, you will have Ri 1 minus Si 1 squared plus Ri 2 minus Si 2 squared. Okay. So, that is the expression. Okay. So, the key idea is you can compute this using a summation, of course. Okay. So, the computation can be done sequentially, it is obvious, right. So, summation one after the other. It turns out you can also do the minimization sequentially. Okay. So, that is the trick in the Viterbi algorithm. The minimization also can be done at every step, okay, and you do not have to remember too many code words, you only have to know 2 power mu code words. Okay. As long as you keep track of 2 power mu code words, maintain a list of 2 power mu code words, it turns out the global minimum will occur within this 2 power mu, and you can be happy about the answer you got. Okay. So, that is the central high level idea, and how it works is easy to describe. I will describe it, and we will not see rigorous proofs, but I think you will see clearly that it works. Okay. So, it is a nice idea, it will work out very well. Is that okay? So, the first thing we will use to translate this into trellis languages, we will distribute this summation over stages of the trellis, okay, and there is a very natural way to do that, right. Remember, the ith input is associated with the ith stage, right. So, the ith output Ri is also associated with the ith stage, and these SIs will where will the SIs be? In the ith stage of the trellis, they will be on the branches, right? The branches will have the SIs, possible SIs. Okay, so you go on each branch and then write down what you compute here, and then you have translated what you have to do into the trellis. Okay, the only thing I have to do next is show you how the minimization can also be done efficiently over the trellis, and that will be the end of it. Okay, so let us do the first translation on the ith stage of the trellis. Okay, so if you look at the ith stage of trellis, okay, so you will have how many states? 1, 2, all the way down to 2 power mu states. Okay, and this side also you would have 1, 2 all the way down to 2 power mu states, and there will be branches. I will take some kind of a generic branch, maybe from, I do not know, where can we take a generic branch, somewhere from here to here. Okay, and maybe it goes from, okay, so maybe that is not a good idea, right. So let's just take some state I to state j, is that okay? I to j, right. This time I was smart, I wrote first and then drew the circle. Okay, so let us take a branch that goes from here to here. Okay, what will be written on top of the branch? There will be a label for the branch, right, input slash output. Okay, so since it is I to j, maybe we call it u, I do not know what shall we call it, ij slash sij, right. So, I mean this is just notation, I think it is clear what I mean, but it is good to write it down also. Is that okay? So, remember uij is going to be just 1 bit, sij will be, well I am thinking of sij as 1 minus 2 times the BPSK encoded form, right. So, it will be 2 a length 2 vector because of a rate half code. If it is a rate 1 by n code, then it will be a length n vector with plus 1s minus 1s depending on what the actual output there was. Is that okay? All right. So, what I will do is I will associate with this branch something called as a branch metric. Okay, what will be, so this I is occurring in too many places, right. So, maybe I will make this the nth stage of the trellis, sorry for that. Okay, the nth stage of the trellis, you are looking at state I to state j as transition. Okay, the branch metric will then be RL1 minus Sij what 1 square plus RL2 minus Sij 2 square. Okay, so this will be the branch metric associated with that particular branch in the nth stage. Okay, so you have to think of this branch metric as some kind of a weight on that branch, okay, or some toll money that you have to pay somebody who is sitting there to go on this branch. Okay, to take this route you have to pay that money. Okay, so some cost associated with, or maybe the distance that you have to travel on that branch, something, some cost associated with that branch or edge or whatever you might want to call it. Okay, and why did I define it this way? Right. So yeah, so I am trying to minimize the sum of terms like this over all possible code words. So, if I have a code word on which this branch was actually used, this will be a term that will participate in the summation. Okay, so that is the idea. So, I am trying to write down all those summation terms in terms of the branches. Okay, so I think that is the first step. Okay, so we have some kind of a branch metric we can deal with. Is that okay? All right. So, the goal now is, okay, so the soft ML task of finding the least the code word closest in terms of Euclidean distance can be written in terms of the trellis. Okay, so what you have to do for that is you have to first use this idea that code words correspond to paths on the trellis. Okay, So, what is a path? Path is basically a sequence of branches. Okay. What do I have for each branch? I have a branch metric. So, what can I do for each path? I can total all those branch metrics on that path and get something called a path metric. Okay. So, that is called the path metric. Okay. So, we will define the path metric, sum of branch metrics on path. Now, this path metric has a very real meaning for us, right. What is the path metric? It is exactly this term, it is exactly this term, this is exactly the path metric for that chosen path, for path corresponding to the code word to S. Okay. S is a valid, well, symbol sequence, not really a code word sequence. S is the symbol vector. Okay. So, it corresponds to a path on the trellis. The path metric of that path exactly equals this R minus S square. Okay. So, that is what I have done with this trellis representation. Okay. So, my task of doing soft ML decoding, of finding that code word which is closest in Euclidean distance from the received vector, is exactly the same as finding that path with least path metric on the trellis. Okay. So, it is a very simple one-to-one correspondence, and that is the first idea in the Viterbi algorithm. Okay. So, the soft ML can now be equivalently written as U cap. Okay. So, remember, the U cap also defines a path on the trellis, right. So, I have to be careful here when I do notation. Okay. So, path of U cap equals argument of minimization over all paths of what? The path metric. Okay. Remember, the input sequence also defines clearly a path on the trellis. Okay. So, I can think of the path corresponding to my decoded input sequence, that will be the argument of the minimization over all paths of the path metric on the trellis. Okay. So, remember, the metrics change for each received word. Okay. Once you get a received word, you have to compute the metrics and kind of load it on that trellis, and on that trellis with those weights you have to find the minimum path. If you get another received vector, what will happen? All these weights will change. Okay. You have to recompute the weights. Okay. So, how many computations of weights do you have to do for decoding each code word? Yeah. So, you have to compute one for each branch. Okay. In fact, you can simplify the computation, it is not, you can do some optimization, but anyway, one for each branch. How many branches are there? 2 times 2 power mu times k plus mu. Okay. So, clearly it is linear in k and exponential in mu, it is not exponential in k. Okay. Once it goes exponential in k, you have to worry about it. It is not going exponential in k, it is only going linearly in k. Okay. So, computing the branch metrics is not a problem, but if you want to compute path metric for every possible path, then there will be a problem. Okay. Once again, you will go back to the same 2 power k. Okay. Right. Because there are 2 power k paths, and for each path, if you want to keep doing this computation again, you are not going to go anywhere. Okay. So, the trick to efficiently do it within 2 power mu is to only compute path metrics for some paths. Okay. So, you will keep track of only roughly 2 power mu paths as you go along the trellis. Okay. And it turns out the best path will always be within this 2 power mu. Okay. So, the question is, which are these 2 power mu paths and how should I keep track of them? Okay. I will give you a simple argument, it is easy to see why this will be true, you can also prove it rigorously if you like. Okay. Remember, I started at the all 0 state. Okay. So, this is the 0 state, and I also ended at the all 0 state. So, this happened at stage 0, 0th stage, and this will be finally at the k plus mu minus 1th stage. Okay. So, that is fine. So, if I look at the ith stage or lth stage, okay, I am going to have, so let us say, so remember there is going to be something on this side or that side, so let us say I pick up this side, there will be a bunch of states. Let's focus on some particular state. Okay, let's focus on, let's say, state I, okay, on the lth stage. Okay, now if you look at paths from the all 0 state at the beginning to this state I in the lth stage, there will be several paths, right. Let's say, let's draw a whole bunch of them. I am going to draw them dotted. Okay, there will be several paths to state I in the lth stage, and once again from state I to the all 0 state, there will be once again a lot of paths. So let's do that. There will be a lot of paths. Okay, I am just drawing a representative sample of some paths, but there will be lots of them. Okay, I do not want to keep track of all of them, that is the issue, right. So if I want to find the lowest path metric path from state 0 to starting at state 0 and ending at state 0, my argument is at this state I only have to keep track of that path which has the minimum metric up to state I do not have to keep track of all of these paths that are ending here. It is enough if I keep track of that one path which has minimum metric up to that point. Okay, so that is the idea, I am doing it sequentially as opposed to doing it totally. At this lth stage, I only worry about the minimum path metric up to that point, but I have to do it state wise, I cannot just do it totally, state wise. For the state I, there will be one path which is the minimum metric path. Okay, I can only keep this and throw away all the other paths from 0 to state I. Okay, why is that okay? The reason is, if the overall final best path that you have were to go through state I in the lth stage, then it will necessarily take this path on the left hand side. Okay, it cannot take anything else. The reason is, from here it would have taken something to go there, and if it took some other path, clearly you can drop that and go to the minimum weight path and get a lower weight path. Okay, so for this simple reason, because you are starting at 0 and ending at 0 and you are looking at the ith stage, you only have to keep track of that minimum metric path from the 0th state to this ith state. Okay, so let me repeat that argument once again, I will do it just in words, I am not going to write it down. If the minimum overall final greatest path, I mean the minimum metric path that you have were to go through state I in the lth stage, then from 0 to I it would have definitely taken the minimum, that partial minimum weight path. Okay, if it, for instance, the argument is by contradiction, if you say if it did not take that path, then what do? You keep the remaining part the same, okay, and then here you flip from the path that it took to this minimum weight path and you would have decreased metric, and that is a contradiction. Okay, so you cannot have anything else. Okay, so it splits this way, and the crucial reason why it really works is you are starting at 0 and ending at 0. If we are not doing that, then it will not work. Okay, you are starting at one point and ending at one point. Okay, so because of that, this works in a nice way. Okay, so I have to now do this for each state. Okay, so each state I have to keep track of only one path, and that is only 2 power mu paths as I go along the trellis. Okay, how you do that efficiently is the Viterbi algorithm. How you do that is the Viterbi algorithm. It's no big deal in efficiency there. You already come down to this efficiency. Okay, so this is the idea behind the Viterbi algorithm. Okay, of course, in the original paper of Viterbi, it is not described like this. It is something else. It is actually a proof technique used for proving something. Okay, it is very strange. It was not even an algorithm at that point. Okay, so the important person who played a key role in making it an algorithm was David Forney. Okay, so his name is usually not mentioned, but I think it is good to know that Dave Forney played a key role in writing it down as an algorithm and explaining it to everybody as an algorithm. Okay, but I think in the world of dynamic programming and other areas, it was known long before. It's not invented by anybody here. Okay, so that's the idea. Okay, so that's the basic task. So let me write down a step by step kind of algorithmic description or pseudo code for the Viterbi algorithm, and only for the Lth stage. What do you do in the Lth stage? I will write that down, and then you will see how you can repeat it, and it is very easy to generalize from that. Okay. So some kind of algorithm. Okay. So what happens in the Lth stage? You have states 1 to 2 power mu, then you also have okay, this is the Lth stage. Okay. So each out of each state you are going to have 2 branches coming out, and into each state you will have 2 branches coming in. Okay. So let me take the jth state here. Maybe its 2 branches coming in are from J1 and J2, okay, I1 and I2, sorry, okay, I1 and I2. Okay, so there are 2 branches coming in. Okay, so this will have one branch metric, that is, maybe we can call it BM I1 to J. Okay, and this will be another branch metric BM I2 to J. Okay. Now, in my algorithm up to the L minus 1th stage I have already done something. Okay. So, which means for state I1 I will be remembering one particular path, okay, and that path will have a partial path metric up to that point I1. Okay. So, that is called the state metric for this state I1. Okay. So, that is what is called the state metric. So, let me write that down. Okay. You have the all 0 state. Okay. Well, I am starting from 1 here, right. So, that is the problem. Okay. So, let us say 1 the 0th state. Okay. So, this will be like the minimum metric path from all 0 state at stage 0 to state I1 before stage L. Okay, so, it is a long worded description for what is maybe easy to describe, easy for you to understand. Okay. So, that will have a partial path metric. Okay. So, that metric is called the state metric for I1. Okay. So, minimum path metric path. Okay. So, this partial path metric is called state metric for I1. Okay. So, we need some notation. So, this minimum path I will denote as what? It is usually called the survivor path. So, I will call it SP at the SP for I1. Okay. All right. So, it is usually called the survivor path, the minimum metric path from all 0 state to I1, and the metric of that path is called the state metric for I1. Okay. So, I have to also index it by L. So, I will put a L on top. Okay. So, both these guys will have state metrics. Okay, both of these states will have state metrics, and the branches will also have branch metrics. Okay. So, the task for this algorithm is to compute the survivor path for J after the Lth stage and its corresponding state metric. That is the only task. Once I describe that, you can simply repeat the task stage after stage for every state and you are done. Okay. So, how is that done? It is done like this, it is very easy. Okay. So, if SM L of I1 plus BM I1 to J is greater than SM L I2 plus BM I2 to j, okay, right. What should I do? Yeah, so you make the survivor path of j as survivor path of I2 and append to it maybe j, right. So, the last one will be simply j itself, okay. So, you come up with this path and then add the j to it, and then state metric for j is after L plus 1 is basically what? SM L of I2 plus the branch metric I2j. Else what do you do? Else replace I2 by I1. Okay. Okay, so the reason why I can do that is the justification I gave before. Once I fix a particular state and a particular stage and I start at all 0 and end at all 0, I only have to keep track of the minimum way to get there. Okay, from there I can worry about what I do later on. Okay, so this is the idea. Okay, so like I said, the complexity roughly is k times 2 power mu, okay, which is much smaller than 2 power k. Okay, so it's really doable. Okay, if you have just even if you have 6 bits for the state, 64 states, okay, 1000 k equals 1000, you can easily do it. 1000 times 2 power 6 is nothing. Okay, on the other hand, 2 power 1000 is something you can't even imagine. Okay, so it's very big. So that's the idea. Okay. Okay, so what's the basic summary here? So soft ML decoding is implementable for convolutional codes. Okay, so this is the major step. Okay, and the trellis played a crucial role. And other thing is the complexity of the trellis. Okay, because we have the definition as a convolutional code, we fix the complexity of the trellis ahead of time. Okay, so we fix mu is 6 or 4 or 5 initially when we design the encoder itself. Explicitly we fix it. Okay, for instance, if you do the other way around, if you start with the generator matrix, parity check matrix, and then try and go to a shift register implementation, that's very hard. Okay, it's not very easy to do those things. Okay, but since we start with an explicit shift register implementation, everything becomes really simple. Okay, so convolutional codes are some of the most popular codes around. Every one of your cell phones have it. Okay, so it's used in several different applications, all the way from outer space to magnetic disk drives, maybe not. Okay, so some other things, it's used everywhere basically. This idea of Viterbi algorithm, it's there all over the place. Okay, of course Viterbi became a millionaire. It's already started Qualcomm and other things. Okay, so my brief comment on the hard ML decoding. So if your channel model became the binary symmetric channel and you have to now do hard ML decoding, what will you change in this algorithm description? Okay, so it turns out the only thing you have to change is the definition of this branch metric. Okay, the branch metric definition here involves a Euclidean distance computation. What will it be for the BSC? It will be a Hamming distance computation. So, okay, so you will have 2 bits received for this particular stage. Sij will be 2 bits. You simply take the Hamming distance between those 2 things. Okay, and every other part of the algorithm remains exactly the same. Okay, nothing else you have to change except that the branch metrics, instead of being Euclidean distance, simply become Hamming distance. Okay, and that gives you hard ML decoding. Okay, so that's the. Okay, I didn't want this.
Sir, how much penalty it's going to incur for us if we don't end the trellis exactly with all zeros?
Okay, I'll make a comment on that. Just 1 minute. Okay. So, hard ML decoding, you have to simply replace Euclidean distance, okay, Euclidean distance in definition of what? Definition of branch metric with Hamming distance, that is it. Okay. So, that is definitely doable, and it can be, it is very efficient also, it is similar in efficiency, 2 power mu is the complexity. Okay. So, the next interesting thing to worry about is some kind of an implementation detail if you want really much lower complexity. So, in fact, I was saying k equals 1000 is not too bad because 1000 times 2 power mu is not a big number, but still 1000 is a fairly large number. If you want to reduce your what to say, I mean VLSI footprint, so to speak, to be very small, you can't really maybe do even 1000. Okay. But if your original length was 1000 and you terminated only after 1000, you have to go all the way to 1000 before you can finish up your decoding, right. So, it seems like a kind of a, anyway it is more expensive than what you would have thought beforehand. Okay. So, what people usually do is they go sufficiently far into the trellis. Okay. So, they will not really go all the way to 1000. So, they would go, if your memory is mu, the rough number is supposed to be 4 times mu or 5 times mu. So, you go some 50 or 100 into the trellis, how much ever your circuit complexity can take. Okay. So, you go as far as that and then you kind of stop there. See, out of all the paths you have, you simply pick the minimum path and then you go back, but you do not make decisions immediately. Okay. So, if your memory was, let us say 6, okay, so you go all the way up to 100 and then you backtrack and do not make decisions on the immediate 50. Okay. You will go from 0 to 50 and make decisions there, okay. And then you allow for this 50 lag, and it is called windowing. Okay. So, you can do windowed versions for efficient implementations. Okay. So, you do not have to really go all the way to 1000 and then come back. Okay. So, you go partially and then you pick among the paths you have the best one and then come back, but do not make decisions towards the end of the path, because you know the end of the path is, so you are not very, you have not terminated, so you are not very sure. Okay. So, you leave some gap there and then you decide after that, and that gap is supposed to be 4 mu or something is good enough. Okay. 4 mu or 5 mu is supposed to be good enough based on experiments. People have run this several times and found that 4 mu 5 mu is good enough. Okay. So, you do that and that simplifies your complexity a lot. Okay. So, in fact, most implementations will do that, only windowed versions are implemented. Okay. And that is hardly any loss. Okay. But if you do not terminate, you will get a huge hit. Okay. In terms of you will do soft ML, that is not a problem, but then your decoder performance will be very bad because minimum distance will be very less. Okay. So, that is the next thing we are going to talk about. Okay. One thing to worry about is implementation details. I am not going to spend too much time on this, except that windowing is an important idea in implementation. Another important idea is making sure that you do not overflow. Okay. So, you have to take care of overflows. Okay. Because particularly if your SNR is low, then these branch metrics can blow up. Okay. So, what people do is, since you are always comparing paths of similar lengths, they would subtract the minimum of these branch metrics and keep only the difference, and that is good enough. Okay. So, those are ideas that you can use. If minimum is difficult to compute, you simply subtract a large enough number after every time. So, those are all tricks that people use to keep the overflow problem done. Okay. So, that is implementation detail. More important is performance. Okay. So, how is performance affected? How do you measure performance? Okay. Okay. So, it turns out the union bound gives you a very nice way of thinking about how this will work, and we will talk about that in the next lecture. Okay. So, time is up. So, we will talk about performance and how minimum distance plays a role in the performance, and all that we will talk about in the next